Oh my gosh, I'm muted. Let me start again. Sorry. Thanks, Matt. Told everyone else to mute themselves.
I wasn't sure how else to get your attention.
It's awkward. I can see all the comments coming through as well now. Anyway, just to start, thanks all for joining today. Again, we are going to run through the AGM first, and then we'll get on to the meeting being given by Dr. Andrew Hart. So the agenda for the AGM is the chair's report first of all, where we'll run through last year's events and also the plan for this year's events, the treasurer's report, the election of the committee, and then straight into the presentation. I'll try and run through this quite quickly. So last year's events, we actually had quite a few. I hope you all kind of managed to join us. We had talks from places all over the world, from Zambia to the North Sea to just down the road. We also managed to have a field trip run by Dr. Dave Giles on Newlands Corner Geological Trail. If you want to see some pictures of that, it's all on our LinkedIn page. So some key highlights was, of course, the field trip itself, and we've got some really good feedback on it. I hope you all enjoyed yourself. But also we had the kind of annual Young Geoscientist competition, which was run by Roberta McAllister from Atkins this year. Onto the plan for 2022. We already have some very interesting talks in the pipeline, including today's talk. We've got some talks on mining by Sandra Etchells from Anglo-American. We've got building foundations for net zero by Sarah Cook at LEAP. And we have some talks on karst geomorphology in Albania by Mox MacDonald. We also again planning on some local field trips by Dr. Dave Giles as well. For those of you that are looking to get chartered recently or soon, in September we'll have our kind of biannual chartership event, and where possible we are going to try and make these presentations face to face, particularly that chartership one. And hopefully in December, barring any COVID related or other issues, we will have our annual Christmas social again. So something that's being pushed quite heavily by the Geological Society at the moment, and something that us as the South East Regional Group are quite passionate about, is STEM. So just as a kind of shameless plug here, hopefully we can encourage some of our members here to have a look at some of the resources available on the Geological Society website. And get more involved with STEM and outreach. This is a particular issue at the moment with the decrease in participation in the geosciences. So hopefully if we can kind of reach just a few schools, a few students in our local area, then we can make a real difference in the future. There's loads of resources on the Geological Society website, including becoming a geology STEM ambassador. So please do take a look at that. And our financial summary this year, unfortunately our treasurer isn't available to join us today, but we are hoping, so we left last year with just under £1,300 in the bank, and we're proposing a grant application of £500 this year, and this is with the aim to have some more face-to-face meetings again. And with those face-to-face meetings, we will try and provide some sort of recording facilities, because we're getting really great turnouts from these online events. And just onto our committee now. It should be 2022 committee. So I will be continuing on as chair, with the aim to hand over to Matt Cook kind of towards the end of mid to end of this year. Matt is taking over as vice chair, so that he can get a handle on what it is that we do. Sarah Cook is staying on as secretary, and Johnny Neville staying on as treasurer. We also have 5 other members to the committee: John Ellis, Ursula Lawrence, Mark Davis, Stuart Field and Sam Marshall, who will all be staying on. Unfortunately, we're saying goodbye to John Race. He's been with us for quite a few years, I think probably coming up to 10 or so. So it'll be sad to see him go. But that does mean that we have some places available. So if you're interested in joining, please do let me know. Drop me a message on an email, LinkedIn, or just on here, and we can get you involved. So is there any objections or questions to that? Nope. Good. Excellent. So I will hand over to Dr. Andrew Hart. He's a colleague of mine here at Atkins, and he is head of our geomorphology division, and he'll be talking today on reading the ground to reduce hazards and risk in engineering projects. So over to you, Andrew.
Thank you, Holly. Let me share my screen. Cool. And then if I do that, cool. Can you all hear me okay?
Yes.
Can you see my screen?
Yeah.
Yay, technology works. Excuse me. Well, okay, well, thanks very much, Holly, for the introduction, and thanks for the invite to give this evening's presentation. And good evening, everyone who's on the Teams this evening. One of these days we'll get back to a pub, I'm sure, but hey, technology is brilliant. So this evening I'm going to talk to you about reading the ground, as Holly introduced, and just trying to sort of skim over the topic and sort of how we can use this sort of idea of reading the ground to try and reduce the hazards and risks on our engineering projects. And I should say, yes, as Holly introduced me, I'm an engineering geologist with Atkins. I'm also a geomorphologist as well, so I can put on whichever hat I feel like. Predominantly my experience has been onshore, but occasionally I do try to sort of work on offshore projects as well. Keep my feet dry though, I hate boats. So a lot of the work I do in the past has been looking at landslides and other forms of geomorphological hazards or geohazards affecting slopes. So this part of my presentation, this is actually a presentation I gave a couple of years ago, but I've sort of modified it and updated it, partly because it was quite interactive in the past, but not so much these days. But essentially, when you look at a photograph such as this is Mam Tor, for those who might recognise it, in Derbyshire. What do you see in that photograph? Now, depending on your background, depending on your training, whether you're a geologist, a geomorphologist, a botanist, or an archaeologist or something, you'll see different things. Different things will catch your eye, and you'll be drawn to them, and you'll see different things. Now, for those who are geologists, you might look at this and think, and if you know the area in Derbyshire, the Hope Valley, you may know that you've got let me just get my pointer. You've got limestone forming a bit of a plateau at the top. So this is the low limestones formation, and it's overlying the EM limestone formation. And limestone in this part of the world is often contains cavities and caves, and it's well known caving area. When I was based in Chesterfield office for Scott Wilson many years ago. A lot of my colleagues used to spend their weekends either climbing or caving on the limestone. And that's overlying the Bowland Shale Formation, which comprises of mudstones, siltstones and sandstones, and that sits in the bottom of the valley. But looking at this, you've got the Mamtor landslide, which makes the area famous at the end of this valley. Very beautiful area to visit, but also quite an interesting landslide. You've got the Mamtor beds poking out within the scarp of the landslide area, and you've got the abandoned A625 Sheffield Road to Capel Frith. And this has now been replaced by a road that comes over the top and through another area there, a very steep road. This road was active up until a few decades ago and then has now been abandoned. But if you're an engineering geologist, say for example, I'm an engineering geologist, Holly's an engineering geologist, and a few people on the call will be, and it's a sort of, we may have a client comes to us and in an area like this and say, right, we perhaps want to rehabilitate the road, or we want to do some sort of engineering project in this area, so some sort of construction. And so that gives us what I call the ground engineering challenge. And that's going to be looking at, okay, the engineering properties of the soil and rock, and what's their lateral and vertical variability going to be? If we're looking at sort of putting structures and foundations into the ground, we need to understand what's going on. There's also the geomorphological processes and geohazard activity. As I've alluded to, there's the Mamtor landslide, there's caves, there's other issues. We've also got groundwater and surface water issues. So if we're going to perhaps build something, we're going to need to look at how we deal with that and how we handle that water. And but above all, when we look at all those different issues, the key question is, what is the implication of those factors on our construction project or our engineering project? And from that, how are we going to investigate the ground conditions? Now, there's a quote by Rudolf Glossop in 1968. This was for the 8th ranking lecture. And I'm sure many of you have heard this quote before. David Shilston, in his recent Glossop lecture, picked up on this as well, and so have many other Glossop lecturers. But it's a really important quote. So Rudolf Glossop, talking about Terzaghi, said he noted that he emphasised the fact that minor geological details may have a critical influence on engineering problems. And also that if at the very start of the project, the geological structure of a site is misinterpreted, then any subsequent sampling, testing, calculation can be a lot of wasted work, labour in vain, as he calls it. And to put it differently, he came to the conclusion that if you do not know what you should be looking for in a site investigation, you're not likely to find much of any value. In other words, if you don't know what you're looking for, you won't find it. And he thought that what you should be looking for is going to be suggested by the natural environment and by the nature of the construction problem that you're needing to be solved. So it's matching up. What's the problem I've got? What's the problem I need to solve? And what is the natural environment telling me? Now, scroll forward to 1997, Professor Pete Fuchs gave his Glossop lecture and he picked up on this topic, and he sort of played around with the idea and put forward something he called the total geological history model, and then he further refined that with others in a paper written in 2000. Basically, he came to the conclusion that, he summarised, the ground conditions of any site are a product of its total geological and geomorphological history. And I've tried to sort of summarise that in that chart there. You've got the geological history, you've got geomorphological processes, but you've also got climatic conditions, both past and present, leading to give you the ground conditions that we see before us. And just what do I mean by that? Or perhaps for those not familiar, the total geological history is basically looking at our sites. We may understand, for example, in the Hope Valley there, you had limestones and you had the Bowland Shale Formation. But it's looking at those materials and thinking, right, looking at your area and thinking, right, what geological materials have I got present here? How are they deposited? Or are they the result of igneous intrusions or metamorphic processes? But also, they were deposited, obviously, perhaps millions of years ago, tens of millions ago, hundreds of millions of years ago. During that time, they may have been subjected to plate tectonics. The UK has floated across the Earth's surface due to plate tectonics over many years, millennia, and sort of moved its position from somewhere near to the equator to now where we find ourselves today. And that gives rise to quite a complicated geological map for the UK, but that applies to anywhere in the world, apart from perhaps if you're in places like the African subcontinent, where you've got a Precambrian shield that hasn't really done very much for a very long time. But those deposition environments that we see will give rise to very different geological rock formations, and those formations will inherit different material properties and material behaviours, and we need to understand what that is. But that's also influenced by the geomorphological processes that are continually acting on the Earth's surface. So, for example, we have the erosion and transportation and deposition of materials, through erosion within mountainous environments, transportation through river systems, and deposition into other areas. So, for example, into river deltas or offshore in marine environments. We have the plate tectonics that may take that material from the deep marine to the top of the Himalayas, where you have limestone. So you've got these processes helping to develop landforms and evolve those landforms over time, and they're driven by tectonics and climate weathering. So climate and weathering. And for example, a good example here in Northwest Europe, and particularly UK, is the Quaternary glacial period, where we had this advance and retreat of the glacial ice sheets, scouring out the Earth's surface and shaping the landscape that we see around us in Scotland and northern England. And also related to that was sea level change, and for example, so we had a talk from Andy Emery last year where he talked about the Dogger Bank and the fact that the North Sea was dry land, and you could walk from the UK to France and mainland Europe without any problems with getting your feet wet. So it's had this impact of shaping. These geomorphological processes have shaped the land around us and shaped what we see. But also that's driven by climate and weathering. So if you look at the planet now, you'll see that it's divided into these different climatic zones. And it's always been that case that there's been some form of climatic zonation across the Earth's surface based on the shape of the sphere. And so with plate tectonics, as those plates have moved, sometimes areas of land have been moved around through different climatic zones. And also if you've got the glacial quaternary fluctuations in climate, those ice sheets have moved those boundaries around, and so those boundaries are often in the northern hemisphere moved southwards. And so at one point in the past, the Sahara Desert was actually a lot more wetter and vegetated than it is now, because those zones during the Quaternary were pushed south. And that also gives rise to the formation of surface materials and soils. So the chart on the right-hand side of the screen here is showing, so here you've got the polar regions on the left of the chart, and on the right you've got the equator. And depending on the level of precipitation, which is the blue line, the temperature, which is the red line, and the rainfalls, and evaporation, which is the grey line, you'll get different types of weathering profile, and therefore the different formation of different types of soil horizons on the ground surface. But then sometimes these soils can develop and then become fossilized, and then new soils develop on top of them, representing the climatic conditions in which they sit. So being able to have an understanding of these soils helps us understand a little bit of where things have come from in the past. So it almost gives us a framework for understanding the conditions of our sites. And we typically, in the work I do, we show these as conceptual ground models. And in other words, we bring together all of this desk study information about our site into a conceptual ground model. Now, this could look like a geological cross section, such as the one drawn here, quite simplistic, but it's taking published borehole data and then trying to make sense of what the ground conditions are showing us. It could be an evolution block model, such as this one, where somebody's tried to understand for a coastal project how sea level rise and fall during the Quaternary has given rise, or perhaps even longer period than that, has given rise to different geological formations, and therefore their interlinked properties and how they vary laterally and vertically. And I thank Holly as well for this photograph of some sketching that she did in Scotland for a project where she's looking at the rock outcrop and trying to understand the structural patterns within the rock. And there's discontinuities, the structural geology in relation to a ground investigation that she was supervising at the time. So these are the different types of conceptual ground model that we can bring to site, and then you build in some of that total geological history that I mentioned. Now, if you're anything like Peter Fuchs, Professor Fuchs, he often did work with Tony Waltham and a gentleman called Jeff Pettifer. And Jeff was an amazing artist, and they wrote this book together, Fuchs et al. 2015. And in there, there's these amazing block drawings that were drawn by Jeff Pettifer. And this is one for the southern UK, and it's an idealized model. But this is Peter and Tony and Walt and Jeff trying to synthesize a ground model, a conceptual ground model that summarizes the geological history, total geological history of the southern UK. So of course you've got the chalk uplands overlying lower chalks and limestone beds. You've got some other sort of geological fraction here, so Paleozoic sedimentary rocks. You've got tectonic faulting. You've then got because of the Quaternary, the glaciers have obviously never reached the southern UK, but their effects did. So we had ice formation of ice wedges, frost shattered rock, potential for pingus to form, solid fluxion lobes, etc. And you've got dry valleys. And so they tried to link the geology with what's happening on the ground surface as well in terms of topography and landscape. And the idea here is that if you can try to bring these models together, they're a really good way of, one, as a project team, trying to understand what is happening at our sites, the geological variability of the ground conditions and what may be there and what may be lurking there that we don't know about and can't see, but also how they link to the topography and what we're looking at. And then you can start to plan your next steps of the ground investigation or your preliminary design, etc. But it's also a great way of being able to talk to your clients. It's a great tool for being able to explain to your clients who may not be technical specialists in what we're worrying about, what we're trying to do. Now, of course, going into the next stages, we can then start to sort of bring in additional desk study information, such as borehole data or whatever is available. And we can then also go out and drill our own boreholes. We can go and do our own ground investigations. But what about the landscape itself? Peter and others were really, when they're developing these ground models, they were very careful to try to depict what the landscape is telling them as well. It wasn't all about the bedrock geology, but it's about the surface geomorphology and about the landscape. So what can we do over there? Well, Professor John Hutchinson, in his Glossop lecture in 2001, talks about geomorphology. And in fact, I'm quite chuffed with the fact that a lot of the Glossop lecturers talk about geomorphology, and some of them were geomorphologists themselves. But Professor Hutchinson concluded that the geomorphology of any site is precious and fragile, the end result of interplay of thousands to millions of years between solid and quaternary geology, hydrogeology, climate process, and the nature of the ground as controlled by its physical properties. However, all too often, it's completely ignored and sometimes even destroyed in a day. People go on site with a dozer and start clearing access tracks so they can build, so they can get in their drilling rigs to do a GI or to clear the site ready for the next stage, earthworks, whatever. And so it's destroyed, gone. And the quaternary geology is neglected. I've been asked to go to sites to do geomorph mapping, get there, and it's like, well, we've prepped the ground for the next stage and there's nothing there to see. But Professor Hutchinson came with this idea of a facility to read the ground springs from the curiosity about landscape features leading to an informed interest in the morphology, geology and behaviour. In other words, he saw it connected with geomorphology, trying to see, can we read the ground, read what's on the ground surface to understand what's happening and what it might be telling us. And he said sometimes it's intangible, not easy to formalise, but he thought there were tools available and there was a vocabulary. And so what was involved? What could we do? Well, in some ways, he answered in his Glossop lecture, he answered his own question, and he identified these topics here. And in many ways, they're very similar to what Professor Fuchs picked up on his Glossop lecture and also in his Total Geological History paper with others. And that is looking at the type of the landforms that you're looking at the surface and subsurface materials, looking at the geological structures, discontinuities, impacts of climate change over geological timescales. Looking at the hydrology and hydrology of the site, looking at the geohazards and other surface processes, looking at vegetation cover. The vegetation can often tell us something about what's happening beneath the surface, but too often it's ignored, particularly by geologists. They just see it as something getting in the way of doing their mapping, and also the impacts of anthropogenic activity. And so, for example, if you look at this photograph from Kyrgyzstan, you can see the area is semi-arid environment. You've got very little, because it's in the rain shadow of the Himalayas in the Tan Shan. You've got very little scrub vegetation. You've got bedrock at surface, and you can see within the bedrock, you can see the discontinuities. You can see the bedding quite clearly. There's faulting and offsets and jointing and all sorts of things going on. You can see the incision of the rivers, and we know because of tectonic uplift, these rivers are incising, and so you get over steepened lower slopes compared with the upper slopes. And then you have this road, and so this anthropogenic impact on the landscape of people trying to build a road through this quite rugged terrain. So far, so I've mentioned a few words, some key words so far. One's geomorphology and the other's landforms. Now, I appreciate not everyone may know what they are, but perhaps I hope you do, but perhaps just in case you don't. What is geomorphology? Well, it is actually the study of landforms. What are landforms? Well, they're the individual topographic features exposed on the Earth's surface. They're dynamic, they're continually affected by Earth's surface processes. Very often, if I talk to some members of my family or friends or whatever, they think the landscape has always been as it looks today, and you can see why. If you look at places like the Himalayas or the Sahara Desert, or you can just have this timeless quality. They've been there forever, but it's not true. They're continually evolving, continually changing. No matter where you are on the planet's surface, the landscape around you is continually changing, and it's trying to get your eye into what those changes are and what's driving those changes and the processes that are involved, and whether it's erosion, deposition, etc. And the other way of looking at landforms is in terms of their scale and the size, and also in their duration within the landscape. So Professor Brunston, in his Glossop lecture in 2002, pulled together this chart where he tried to depict different types of landform. So mountain areas up here, and you've got channel infill here, and rainfall impact craters and rock avalanches at this end. And he's looking at the size of the landform. So obviously rainfall impact craters are really quite small, mountains are quite large. So times of the size of mega relief, or the order of type of relief that you're seeing, but also the duration in which, one, they take to form, but also they last within the landscape. Because mountains last so long, there's so much evidence to be able to see, and you can get a better understanding. But some landforms form very quickly and then are destroyed almost just as quickly by continual Earth surface processes. And so that sometimes skews the record. But by understanding this sort of chart, we can understand what these landforms might be telling us about the processes acting on them. And then Professor Griffiths and Dr. Stokes, both from University of Plymouth in 2008, wrote this paper where they tried to characterise different landforms into different categories. And they saw those four key types: structural and or volcanic, weathering, erosional, and depositional. And pretty much they say what they mean. Tectonic activity resulting in mountain building, folding, faulting, uplift, tectonic activity, processes such as volcanic intrusions, eruptions, etc. on the Earth's surface have a big impact on the landscape. The weathering, creating in situ decomposition and disintegration of rocks. Erosional landforms such as rivers that transport that by either wind, water, or gravity or ice, and then the deposition of those of that same sediment. And I've just got some example pictures here, sort of showing mountains building, glacial valleys in the Swiss Alps, so erosion caused by glacial activity, rivers such as these in the Himalayas, where you've got braided channels depositing vast quantities of sediment from the Himalayas. I mean, the mountain front is literally just behind me, 180 degrees, and this is looking south into the Indian plains. And you can, this river's not in full flood. When it is, it's about 2 kilometers wide, but you can get a feel for the braided channel. And this is a photograph from Holly again, sort of from Sierra Leone, showing the formation of residual soils so weathering of the bedrock to form these residual soils and also duricrusts. Now, often when you look at landscapes, some landscapes can be quite simple, sometimes they can be quite complex. This is from the Himalayas, and you can see it actually combines several elements all in one area of these different landform categories. We've got obviously Himalayas, tectonically active, they're being uplifted continually, but also at the same time they're being rapidly eroded down. Lots of erosion going on, particularly in forms of landslides. You can just get your eye and you start to see all sorts of landslide scars through the photograph. There's a lot of soil erosion, and there's also incision in the rivers. But those rivers are also transporting a lot of material from further high up in the Himalayas through, this is the middle Himalayas, I should say. This is the Siwalik, so the locals will actually say these are not mountains, they're hills, only 1,000 meters to 1,200 meters high, so taller than most of the UK, but they're still foothills in the Himalayas. But these river systems are carrying and depositing, even in this area, large quantities of sediment. And that's something that's important to understand, that rivers, so I mean, I really enjoy working in mountain environments, but one of the key things as a geomorphologist that I need to always understand is what are the rivers doing? Because rivers can often tell you a lot about the landscape you're in, how active it might be, whether you're in a predominantly erosional landscape or predominantly depositional landscape, etc. So, I mean, you've seen this picture before. This is from India, looking at a braided river system, but this is a small channel in the uplands of Georgia, where you've got this mountain stream, but again, it's near a mountain front, not a very big one, and you've got this braided channel coming through, and it's moving around, and there's a river terrace here. And then, of course, you can get wadi systems like this one in Algeria, where it sees very little water. You may get a flood event going through there once every 10 years, 20 years or something. When it does, it's very dramatic and it will deposit a lot of material. But the rest of the time, it's actually through wind erosion that the sediments moving around. This is Arundel, south coast of the UK, thanks to David Shilton, who took some photographs from an aeroplane when he was flying over once. Doing some archaeology in the area, but you can see the floodplains and you can see this one meandering channel. So it's a very low energy system. This is a very high energy system. And this is a moderate energy system, but this is a low energy system. The river's meandering to the coast, moving through, tends to be depositing material more likely than eroding, similar to, in some ways, to this one. Back in the Himalayas, and this is in Tan Shen, two different types of river system. This is predominantly ephemeral again, very little water apart from in storm events, and then you might suddenly have all this bed load is being mobilized, and there's a lot of heavy large boulders in here, and they'll all be mobilized in one go. And the same in the Himalayas, but these are not ephemeral rivers. They nearly always have water in them, but they're scouring away at the hillsides, causing some of the landslides, but at the same time scouring and depositing at the same time. So rivers can tell you a lot, and that often is because, but the first thing you have to understand is where you are within the drainage system. Are you up in the mountainous terrain or near the headwaters, where predominantly they're going to be erosion driven? This is going to be eroding into the bedrock, eroding materials, and starting to transport it downstream. You then may find yourself in the mid zone, which is the transition zone, where you may get some erosion and you may get some deposition, but on the whole, sediment is being transported through that area. And then you get to the depositional zones, which are much closer to the coastline, much lower energy. You may get meandering systems, you get oxbow lakes, you get deltas, etc. As sediment's been deposited very slowly before it moves out into or gets deposited offshore. And this schematic over here is just to show you what often the sort of an indicative of the slope sides, or the river of the river banks, sorry, steepness of the river banks, I should say. So up in the source areas, in the mountain in front, you're very steep slopes. By the time you get to the areas and depositional zones, you're going to have very gentle slopes, but with river terraces either side. So think back to the River Arun, or even some ways the River Thames in London, etc. The other thing that always fascinates me, and that perhaps comes from my background in remote sensing, where I've done a lot. I started my career as a remote sensing specialist, doing lots of interpretation of air photographs, and then going into ortho photography, and that was drainage patterns. So based on the tectonic activity of an area and the geological history of an area and the actual geology of an area, you can sometimes see very distinct and very different styles of drainage pattern. And if you can identify, look at the area, across an area and identify what type of drainage pattern you have, you can start to get a feel for how active an area is, how the landscape is behaving, how it's changing, how it's evolving, and what might be driving that activity. So it's always interesting to understand what that drainage pattern is doing, and then linking it back to where you might be within this sort of system. But then the other thing that's always worth bearing in mind is the human activity, human impact on our landscape. As depicted with Stonehenge here, humans have been playing around on the Earth's surface for millennia, and we've always had this habit of trying to change the landscape around us, sometimes for the better, sometimes for the worse. So if you look around the Salisbury Plain, you see in other parts of Europe and other parts of the world, you'll see these ancient sort of burial mounds and irrigation channels and all sorts of things going on. More closer to home in Cornwall, we have and other parts of the UK, you'll get the mining history. So this is some spoil heaps from the China clay workings in southern Cornwall, and now they've been regraded and revegetated to look like this. And who knows what geomorphologists might think of these in 200 years' time when they've been degraded further and trying to work out what how they fit in the landscape. And then, of course, in Asia, we're all familiar with photographs of the paddy terraces and river and rice paddy fields. And just to give you a clue, here's some farmhouses for scale. And these type of paddy fields will often go all the way from up a slope, sort of 500, 800 meters up a slope, perhaps even more in the Himalayas. So very intense farming method, very labor intensive as well. But they also rely heavily on irrigation canals and channels being dug into the hillside. So very much a modified terrain. So that's hopefully just to give you some idea of landforms and landscapes and what we can try and tease out of them, what we can try and see within them and understand from them, and how we try and tease out what's happening, what processes are happening, and what we need to keep an eye on. But how best to capture this information? Well, one potential method is through the use of geomorphological mapping. There are a couple of others, but I won't go into those tonight, such as terrain evaluation mapping, which is something else I get involved with a lot. But tonight I'll just focus on geomorph mapping. This is a mapping scheme. This is a diagram, originally produced by Crute and Griffiths in 2001 and updated by Fuchs et al. In 2007. And then I've had their permission to update it again to try and refresh some of the colour scheme. But the idea is this is for a river system. This is a river valley in Devon. This is the River Axe. And you've got the underlying bedrock geology, and then you've got these landslides cutting in onto the Earth's surface. And by using the symbology here, you can start to try and pick out these different features. So this little terrace bluff at the bottom of the slope is here. You've got this elongate flow and springhead sapping coming through here, and that's this feature coming through here. And then you've got some small landslides and slumps on the surface, and you can just pick these out through here. And then you get to the top and you have an 8-head deposit, and you've got larger bluffs and escarpments at the top where you have the green sand, and that's picked out by this symbology here. So this is actually, in true sense, a morphological map. It's not actually geomorphology, it's morphology. So we're just looking at the shape or morphology of the ground surface and trying to understand what the key features are, the slope angles, etc. And this is a systematic way of recording the shape of the ground surface. Now, geomorphologists wouldn't normally leave it like that. We'll take it on a bit further. So again, here's another replication of that morphological map, but we've coloured it in so you can link it to the geology slightly more easily. So the grey at the bottom and the purple at the top. But then we get into something called a morphographic map, and morphochronological maps and morphogenetic maps. And the idea here is, with the morphographic map, is to try and understand the processes that are acting on that slope. And the morphochronological map is trying to look at the ages with which things are happening. How old are some different parts of the landscape relative to other parts? Can we link it to glacial periods or to bedrock geology, etc.? And then we also have the morphogenetic map. In other words, is it moving? Is it stable? Is the material suitable for aggregate? Is it a landslide that needs to be stabilised? So by bringing these different types of mapping together, we can start to get a more detailed picture of the landscape and what we're trying to look at. So how do we go about doing that? Well, traditionally, a lot of people might have done field mapping, such as my colleague here on the Isle of Wight looking at tension cracks. But actually, we have a whole host of different technologies and data sets that we can use. Some of them, actually, this is aerial photograph stereoscopes. These were invented by the Victorians, so well over 100 years old technology, but still really quite useful today, and really powerful way of looking at vertical aerial photographs. But we can also collect that imagery using drones, using satellites. So this is a black and white satellite image. This is an infrared. We've got LiDAR data. We even have bathymetry data, so we can do offshore geomorphological mapping. And this is for an area of the English Channel that we worked on a few years ago in Atkins. So there's a number of different examples of geomorph mapping in the literature, and I would also say one of the best ways of learning to do geomorphological mapping is to look up some of the classic examples by people such as Bill Dearman, Peter Fuchs, Dennis Bunston and Gareth Hearn. So this is from South Wales, the Taff Valley Trunk Road. This is from Nepal and the Durandang Kuta Highway, or the Koshi Highway as it's called. These guys really led the way in developing this technology for engineering projects. Geomorphologists, as geographers, were often mapping, but the application of it for engineering projects is relatively new, sort of from the last 30, perhaps 40 years. But I would say, these papers are well worth reading, studying, and trying to copy in what you do. And we can use geomorphological mapping for a host of different things. I would like to go into these in a lot more detail. One, don't have the time, and two, I don't always get permission from my clients to talk about the details. So I'm just going to sort of show you how we use geomorph mapping, or how I used it in the past. So, for example, this is a project in near Bath, where we were looking at some the impacts of landslides around an escarpment area. Now, the landslides are very subtle. These are very shallow solid fluxion lobes and mud flows, also earth flows. Very shallow features, very subtle, and they could easily be missed. But by going around and doing detailed, systematic geomorphological mapping around the entire area, both sides of this plateau area, we could then start to work out which parts of these slopes were more stable and less stable, which parts were more prone to movement, and what was perhaps controlling that movement. And so we can get an understanding of the natural slopes and what was going on, and then how that could affect the engineering works that we were doing. We can also use it for monitoring. This is for a motorway scheme in the UK. You may look at that slope, and I imagine a lot of people have driven past this slope and don't even realise there's a landslide there. So very subtle features again, and so there is a very large mud flow, earth flow in this field, very subtle, but very quite large. And that's this one on this area here. So easy to miss, but with the geomorph mapping, we can go out, we can use the LiDAR data and then field observation to produce a map like this, get a feel for the extent of the landslide, how active it is. And then by using drones, we can do repeat surveys and then repeat the mapping exercise and understand which parts of the slope are moving relative to others, and therefore identify which bits are moving quicker and slower, and therefore pin down what might be causing it, what might be causing that activity, and therefore what can we do to design mitigation measures for that. So where do we put the drainage? I mean, without this sort of information, you would look at this slope and go, well, where do I put the drainage? Where do I put any other stabilization methods? But this mapping, it helps us pinpoint those areas. And then this is another example of looking at actually active slope failures. So here the slopes have failed, and the client wanted to know, well, what's happened, where's it happened, why has it happened, and how's it going to impact my asset in the future? And so by doing a combination of field mapping and also using UAVs again, we could undertake some detailed mapping very quickly over a very large area, very quickly, and get a feel for what was the overall geomorphology of the slope, what's the overall geology, but then which parts are moving more actively, and why that might be the case, what might happen next, were there areas which were creeping but could fail next, were there any early indicators of potential failures, and then build up a model that we could use to assess the hazard and risk that these landslides posed to the assets that were there. And now bringing back to BAM Tor, so having shown those examples, I'll come back to MAM Tor and sort of try to bring things to a close. So this is a geomorph map published by Wolfstra et al. In 2007 in QJGH, and this is a map that they created using photo interpretation of aerial photographs. There's a whole selection of aerial photographs from the 1990s. So it's a great example of a geomorph map. So you've got the landslide extent here, and you've got this symbology showing the scarp and the toe of the earth flow. You've got the old road that comes through here, and they've tried to map out where the trees were and different field boundaries, etc. And they also show where the tension cracks are, where you've got seepage lines, etc. There's a lot of information in there, and after a while it's difficult to start with, but you can start to get your eye in. So I'm just highlighting a spring line, etc. through there. So this sort of mapping is useful to try and capture what's happened, what's going on, and what's happening in an area. But what does that actually mean? Well, if I go back to this, what's strange going on, we can then start to identify certain things in the landscape. So, for example, Hope Valley It's a glaciated terrain, but is it also a post-industrial landscape? So obviously the area has been glaciated. You've got glacial features within there, scour to forming the valley, but also it's had an industrial past. You've got old mine workings that present, and there's a very large cement quarry just to the east of where I'm standing, and it's very active and a bit of a blot on the landscape, but useful for the local economy. You've got the limestone karst, you've got dissolution features, as we mentioned earlier. We've got the shale formation, and we then overline that with Quaternary heads deposits. But are there solifluction lobes within that? We've got the main landslide, but what about within there? We've got the Iron Age forts, as I said. So as well as the post-industrial heritage, there may even be an archaeological heritage as well of stone rows, burial mounds, and other things that may distract us from what we're trying to understand in terms of the overall geology. We've got springs and streams, and this is all bringing water through, and that geomorph map that I showed you highlights it. But that means that some parts of this area are very, very wet, and you get a lot of water flowing out of these cliffs, even on a dry summer's day. And so if we're going to put an engineering project in here, we need to understand where that water's coming from and perhaps capture it into culverts and get it away from our project, because that water is going to continually help with landslide activity within this area. Another is vegetation. What does the vegetation tell us about the ground conditions? I mentioned this at the beginning, but as a geomorphologist, I often get quite interested in what is the vegetation cover of an area? What is it telling me? I've done aerial photography surveys and used satellite data in areas where I can't see much apart from the vegetation cover. So I need to try and use the vegetation to help me understand what is the potential geological ground conditions. Is it free draining? Is it poor drainage conditions, so clay rich or granular material? Because that will give rise to different types of vegetation cover. Also farming practices, that can sometimes indicate to us whether there's good quality ground soil or poor quality soil, and there's perhaps reasons for that. And also can help us understand in terms of slope stability issues as well. Farmers don't tend to like ploughing over landslide material. So by bringing this all together, we start to build that picture of what's happening at our site. And of course, and that's what we can try and capture in our geomorphological map that I showed you on that last slide. So to summarise, I know I've tried to bounce through this quite quickly, and I could probably talk for hours on this subject, but I don't want to take up all your evening. So, as I said at the start of the presentation, as engineering geologists and ground engineers, we have a challenge. Whenever we get to a site and we're trying to think about what a client may be wanting, so construction of a new asset or maintenance of an existing asset or monitoring of an existing asset, or responding to slope failures and trying to understand what's happened in the past and what could happen next. The idea of the total, we have all sorts of questions that we need to answer. And Fuchs et al. Put forward the idea of the total geological history model, and the idea of bringing together the different aspects of the geological history of the site, the geomorphological processes and the climatic conditions that have acted on that site, gives us an understanding of how that site has got to where it is today. And add to that human activity. What have we as people done to that site that gives rise to what we see before us? And one of the key tools in helping us understand that is the ability to read the ground. And by being able to do that, we can then start to better understand those factors on the right hand of the screen, the range of material properties, the geohazards that might be present, as well as the other geoengineering constraints, such as drainage conditions, poor quality soils, things like collapsible soils, what our investigation strategy might be, how are we going to approach it? Are we going to do trial pits, boreholes, geophysics, etc.? And what are the implications for design and managing the risk of that site? And I think hopefully I've shown that Professor Hutchinson, so he developed this vocabulary of trying to understand the site, and hopefully I've shown you very, very quickly what some of these vocabulary can look like and the sort of considerations we need to make when considering them. And sort of the clues that we're looking for within the landscape and trying to tease them out. And also hopefully that I've shown there is toolkits that we have, as well as the vocabulary, there's a toolkit we can use, and that is conceptual ground models, really quite important tool that we have in helping us understand our sites. We've got the ability to use remote sensing information, we've got field mapping, and we've got geomorphological mapping. But Professor Hutchinson in his paper also picked up on one thing that I think is really important, and that's the ability to facility to read the ground springs from curiosity about landscape features. We all need to be curious about the landscape we're working in. Too often I've seen projects where people have just jumped straight into trying to understand the bedrock geology, looking at borehole logs, looking at trial pits, looking at spreadsheets, and there's no real curiosity about actually what happened to get to that site, to develop the site that we're looking at. But it's with that curiosity we can start to piece this jigsaw puzzle together and make better sense of it. I just want to finish by thanking a lot of colleagues who've helped me. This was part of a much bigger presentation, but I thought I'd still mention them. So thanks to Atkins for letting me do the talk, SERG for inviting me this evening, various colleagues who pictured here who've helped me in my career. I won't go through all of them, but obviously some of the key ones I suppose would be people like David Shilston, who with Atkins, and some of my colleagues at Atkins who I've pinched photographs of or pinched ideas from while preparing this presentation. I've got a reading list. I won't share that for too long, but if anybody was interested in some of the references I've mentioned, get in touch and I can point you in the direction. And on that note, I'd like to finish. Thank you for your time this evening. If you've got any questions either now or whenever, please reach out to me through LinkedIn or whatever, and I'll see if I can help answer them.
Amazing, thanks Andrew.
No worries.
A virtual clap for you. Does anybody have any questions? Oh, dead
Stunned everyone
silence.
into silence. Well, no, if you're too shy, ping me an email or get in touch via LinkedIn, and I know some people do get a bit shy in meetings. So.
Excellent. Okay, then, if there are no questions, we'll leave it there. Thank you, Andrew, again. Thank you, everybody, for joining. Hopefully you can all join us for our next meeting next month. And take care. Thanks, bye.
Cool. Cheers all. Bye-bye.